All right. So last time that we were together, when was that? Tuesday. I am. Yep. And so if people aren't here, they can just watch it. Yeah, that's the goal. It's a video, a screencast of my screen. So it doesn't see like up my nose, but it, yeah, listens to what all of you are saying as well. Yeah. All right. So last time we were together, we did a big example at the end before we had some time to do corrections. What was that big example all about? Do you remember?
When you took the basketball and Gerald stopped it. And about the poles and the forces.
The poles and the forces?
Or like the forces of on the ball at certain times.
Yeah. So we had 4 different examples, right? Do we call them like A, B, and C and D or something like that? I don't know. Something like that. And tell me about them just real quick. We're not going to take a lot of time to do this because you have it all written down, but I don't have it on my OneNote. So talk to me here real quick. What forces were at play in A? Earth on the ball and ground on the ball. Which way did the earth go? Down. The force, oops. And then the ground went which way? Up. Was anything touching the ball besides the floor and the air, I guess you could say, in this one? No? Tell me about the motion of the ball or the lack thereof. No motion. Oh my goodness, this is going to be fun. No acceleration. And what did we decide about the net force? 0. I don't know why this is being so goofy. All right. In the second case, what was happening? What was I doing? I pushed on it. So it was the same picture. It had the earth. Oh, excuse me. Make that purple. There we go. And in your notes, ladies and gentlemen, if you don't have them labeled earth on ball and ground on ball, I want you to do that, okay? Those words, just like that, every time. Not because I'm trying to be mean, but because I want it to stick in your head that it's something pulling or pushing on the ball, okay? The force of the ground on the ball. And then was there anything else pulling or pushing on the ball? My hand was pushing on the ball, right? It was. It was pushing in that direction. So you can call it the force of the hand. You can call it the force of carbling. You can call it the force of whatever, but it has to be an object, right? Force of object on object every time. Tell me about the motion of the ball in this case. Same as the first one? Is it at rest? No, it's speeding up, right? Which means that it's accelerating. The acceleration is not 0. You could even say that the acceleration is greater than 0 in that case. Tell me about the net force. It's definitely not 0. Come on. It's like it wants it to be 0, but it's not. There we go. Okay. And as you look at these, ladies and gentlemen, I want this to become intuitive to you that in this case, you've got 2 forces that are pulling against each other, right? They add up to 0. In this case, I've got these 2 that are pulling against each other. These 2, the up and down ones, are going to add up to 0, but this one is an extra force, right? There's something extra that's pushing it that way, and that's the direction it's accelerating in too. That's not a coincidence. All right, tell me about C. What was going on in C? Same as the first one. The force of the earth on the ball and the force of the ground on the ball. Tell me about the motion. It is moving, right? This is when it was rolling along, okay? It's moving, but is it moving faster or slower or the same speed the whole time? Same speed? It's not speeding up. Oh. So it depends on how technical you want to get, right? So technically, there is some friction, right, between the ball and the floor. And if I just let that ball go forever and I knocked down that wall and I took out the carpet and I just let it keep going and I knocked down the neck, like it wouldn't go on forever, right? Because there is friction. But if we imagine like a bowling ball, you know how they like shine them up so that there's very, very little friction between that and the, how many of you guys have gone bowling before? Yeah? You know that line? If you step over that line, have you ever done that?
Yeah.
What happens if you step over the line? Boom, boom, right? Why? It's waxed. It's like super smooth, right? They try and get as much of the little like dust and grease so that there is very, very little friction, like minimize it as much as possible, right? So we're going to imagine most of the time until we really technically start talking about friction. Are you okay? Apparently I should.
My dog's girlfriend wants to put on the line and she found my friend.
In the gutter? Oh dear. That's embarrassing. Awkward. Uh-oh. Yeah. Yikes. Sorry about that. Yeah. Done and done. Anyway, okay. So in all of the physics we do, until we formally start talking about friction, and until we formally start talking about air resistance, we are going to assume that they are zero. It makes life easier. We like to keep our lives as easy as possible, right? So we're going to assume that there's no friction. If there's no friction, then is it fair to say that we're moving at a constant speed? Maybe I can write it, maybe I can't. I don't know. We'll see. And the acceleration is zero. Silly pen. The acceleration is zero. You're like, I got this, Carbling, but I'm glad because this is like the foundations for everything else. And the sum of the forces, you add them all together and that equals zero. And then at the end, what happened? Stop, right? There was a force that was another force that was applied to the ball. This is the force of the earth on the ball. Is the ground still acting? Yeah, still pushing up. And now we've got a force of Gerald on the ball, okay? One note that something we didn't technically write down last time, but you might want to make a note of, is Gerald, it looks like from this, like he's pulling on the ball. Where was he standing? He was standing over here. So sometimes it's really tempting to want to draw the arrow like that. Does that make sense? Because it's like pushing or like stopping the ball like that. But when we draw these pictures for consistency and so that we can always understand what's going on, we're always going to draw the arrows coming from the object, pulling in the direction that it would be pulling. Okay, that's just one of those little things to know. So we're not going to write arrows like this. Okay. And what was happening to the ball? Was it speeding up, slowing down, or going the same speed? Slowing down. The acceleration was not zero. In fact, in this case, it was less than, right? Because it's going the opposite direction of the motion. The ball was going this way. The acceleration was going this way. And the acceleration was going this way because what else was going this way? The force was going that way. Yeah. Add up all the forces, and when you add them up, they're not zero. They are going in that negative direction. Life is good? Now we just relived our time together on, what was that, Tuesday or whatever? Yeah, okay. In what we have done right here, you have done what Newton was lauded for in his first two laws of motion. Oh, Isaac Newton, you're so amazing. No. Was he the first person to roll a basketball across the classroom floor? No. Imagine, right? Cave people could push boulders across cave floors and see the same thing. Are you with me there? Okay. So little cave children could write down these same things on the, on their little, I don't know, whatever they write on. Okay. It could happen. This has been done for thousands of years. It wasn't Isaac Newton's brilliance that made this true. You with me there? Okay. You know how I feel about him. I just want to make that really clear. Okay. Well, I will. I will. Don't you worry. Okay. Like with a dartboard on it. Yeah. I hate Isaac Newton. No, that's hate is a strong word. I don't hate Isaac Newton. I just don't think he's all that. All right. So this is what I'm going to call it, ladies and gentlemen. I'm going to call it Newton's first and second law of motion. One of the other things that I don't like about it, besides the fact that Newton gets all the credit, is that really it's not two things, it's just one. It's two cases of the same rule. Okay? The same rule, if this, then this, if this, then this. That's all it is. Okay? That's all it is. So here it comes. Here it comes. We are as smart as the genius himself. Here we go. If, oops, I'm going to write this more nicely than that. If the sum of the forces is equal to 0, what do you know about the object's acceleration? It's 0. Yeah! I'm going to start calling you Newton. You got it.
Isn't that like not a compliment? I forgot that.
No. I'm going to call you better than Newton. That's a good call. Yes, yes. Yeah. You are way smarter than Newton. Yeah. If the sum of the forces is equal to 0, then the acceleration of an object is equal to 0. I'm going to put some units in there just so that we can keep ourselves honest. I'm going to cross that 0 just so that it doesn't look like the word on. Okay. So if the sum of the forces is 0 newtons, then the acceleration is 0 what? Meters per second squared, just like they always have been, friends. Yep. Okay. Does the object have to be at rest? No. It can be at rest, or it can be what? Moving at a steady pace. Yeah. So I'm just going to put that in parentheses. Either at rest or moving at a constant, I'm going to say constant velocity. If the sum of the forces, if you add all the forces acting on something and it adds up to 0, not going to accelerate. On the other hand, if the sum of the forces does add up to 0 newtons, then, ladies and gentlemen, let's make some sort of big, overwhelming observation here. What? If the sum of the forces is not, that should be a not, shouldn't it? You're like, what is that? Is not 0. The object is what? Ding, 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 ding. Yeah. How's it going? Easy, right? Is that like mind-blowing or surprising or anything? I mean, like, Yeah, we're okay. Sweet. Okay, so that is Newton's first and second law of motion. We'll get into a little bit more mathematical stuff that goes into this second part in a little while. Okay, but if you can remember this, life is going to be good. All right. I've got a couple of ranking tasks that I want to work on because Janelle has been missing them. She's been sending me little emails saying, Miss Carbling, when do we get to do ranking tasks again? That's not really true, but now she'll think about sending those. Yeah, okay. So these are pretty, I don't know, we'll see how they do. We'll see how we do. All right, ready?
Do you want to start it out or don't?
I just take a look at them and then you can just make a little note. Yeah. You don't have to write them down because now you'll have this, you'll have access to, you can just look at it whenever you want. You can. This, yep, I'll assuming I get it, yes, but I will, yeah. If I ever don't post something and you are looking for it, just send me a message, be like, hey, and then I'll do it right away. Absolutely. All right. Here we go. So here's the situation. Oops, hello, there we go. We've been missing them, here they come. Various packages with different masses are moving at a constant, on a constant speed conveyor belt. Okay? At the instant shown, all of the packages have the same constant velocity of 2 meters per second directed to the right. So they're all moving this way. The packages do not slip on the belt. All of the masses are given in the diagram in terms of m, the mass of the smallest package. The question says to rank the magnitude of the net just means the sum of the net force on each package. Take a look at that for just a minute. Think it through, look at what you have written down in front of you and read it carefully again. I will tell you that the answer is not cannot determine. There's a one cannot determine. Do you want to talk about it with your table mates?
Yeah.
Talk about it with your table mates. M is like the mass. So it's like, you can call them like 2 kilograms, 4 kilograms, 3 kilograms, etc. It's just they're all in a multiple of that mass.
Yeah.
All right.
But you're always. Yeah.
How we doing? Do we have an answer?
Yeah.
Yeah, Dylan says yeah. Do you want to share your answer?
All the same.
You say all the same?
Yeah.
With confidence?
Some.
Okay. The old version of these had a thing on the bottom that said rank the amount of certainty that you have, like 0, like 1 to 5, and like, which I think was interesting. It was just another thing to do though. Yeah. So some like you're kind of like a 3 on the scale of 1 to 5.
Yeah.
Okay. Janelle?
Okay. So I think they're all the same, but I think they're all 0.
Oh.
But
I didn't even see that one.
if we're technically going by the law thingy, doesn't a conveyor belt go at a constant speed?
Yeah, it says goes.
Not all conveyor belts, but this one does say.
Okay. So that if there's no acceleration, then they should all equal 0, right?
Mhm.
That's what I'm thinking.
So I agree with you, kind of both, that they're all the same and it's all 0 because 0, for one that says the net force is 0, that means there's no acceleration, and also says that it's either at rest or moving at a constant velocity, and that says that it's moving at a constant velocity. So if you look back to the law, it says that the net force is 0.
Yeah. Seem reasonable?
Mhm.
Yeah, nice work. Yay, good show. That wasn't terrible, right?
I'm like wrong.
No, it's right. That's exactly right. Yeah, they are all 0. The key word here is what? Constant velocity or constant speed or yeah. Where it's not changing speed, so it's not accelerating, so there's got to be no net force. That's it. That's all there is to it. All right. I don't want to do another one of those. I want to go to some problems, but before I do that, I want to come back here and write down a couple of things. A couple times ago, we were talking about types of forces. We talked about gravity, and we talked about contact forces, but we didn't really define anything else, did we? I can't remember.
Yeah, we talked about electromagnetic.
Oh yeah, we talked about those other those spooky action forces, right? Do we talk about any other like specific contact forces at all?
No.
Okay. So I want to do that just for a minute here because we're going to do a couple of pictures and problems, and I want to write down some problem solving stuff here. So when we're solving force problems, a couple of things that you need to know. One is something that we've already started doing, and we've been doing it without me telling you officially, but now I'm going to tell you officially, that one of the very first things that you need to do every time you're doing a force problem is this silent P up here. Okay? It's a picture, but it's a very specific kind of picture. So for force problems, the first thing you're going to do is called a free body diagram, which is a very fancy term for a drawing with arrows. That's all it is. Free body just means it's just that object, so you don't have to draw the rest of the space, okay? A free body diagram, I'm gonna call them FBDs a lot because I'm lazy. Except I can't write that. Oh my goodness, this is ridiculous. A free body diagram is going to have the object, and it can just be drawn as a dot or a circle or a square. It doesn't have to be nice and fancy, okay? And it's going to have all of the forces acting on that object. Not all of the forces in the world. Is it hard to read? Are you having a hard time? Because I'm sorry. No, you're fine. I just want to make sure.
It says all, right?
It does.
Okay.
I wrote it like 3 times. I just need to get a new battery, I think, again. I don't know, because it's really ridiculous, isn't it? Mm-hmm. Yes. All the forces acting on that object, only the ones on that object. So you know how I've said it's the ground on the ball and the earth on the ball and the hand on the ball. Do you notice how they all say on the ball? It's because they're all acting on the ball. Okay? That object. So I shouldn't have one that says ball on the earth in a free body diagram. Earth on the ball is right. Yes, but not ball on the earth. That one's important later, but not yet. Okay, so that's good to know. The other thing that I want to tell you is that in general, the length of the arrows should be indicative of about the relative strength of them. So what I mean by that, so let's say the length should indicate the magnitude, which means size, right, of the force. So for example, on the ball that we were just talking about, if I draw the force of the earth on the ball like this, I wouldn't draw the force of the floor on the ball like that. Why not? What does that make it look like it's doing? It's a greater force. So what would happen to the ball? It'd go up, right? Yeah, or so, yeah, something that's like rising up from the floor. Yeah. and I'm not gonna get my ruler out and like make sure that to the millimeter they're the same length. Not gonna do that. Okay. But you want them to be about the same length. So that it's just kind of a, and then the directions, obviously.
Wait, so do you always want them the same length pretty much? We're not gonna have to draw like the force of the earth on the ball is bigger than the floor.
So, let me give you an example that I think will answer that question. So let's say that I'm going to do a box instead of a ball because it's easier to think about. And I've got the force of the earth on the ball. I've got the force. Oh, not ball, box. Thanks for keeping me honest. Of the floor on the box. And then I've got like the force of the, I don't know, person on the box. In that case, this force is a whole lot bigger. And maybe there is friction in this problem, but maybe the friction isn't enough to hold it back. So if I have it like the force of, I'm going to say the floor on the ball in this direction, that's my friction. Thank you. Okay. This would then indicate that this one is winning or it's bigger. So it's going to move that way. Does that make sense, Maddie? So I don't want to say that all the time your forces won't be the same length, but much of the time they will. If it's not accelerating, then they definitely will be. Fair enough? Okay. All right. We're going to do a problem like this. And so now we're going to add in some numbers. Oh yeah, we're going to add in some numbers today. Yay! And in order to do that, I need to write this down first. We need to write down a couple of these things. We're going to write down the force of gravity. Force of the earth on an object. Come on, stinker. O-B-J-E-C-T. There we go. Okay. The force of the earth on the object is also known as the force of gravity, right? That's what we've been calling it before. Oh my gosh. Okay. The force of gravity also has another name, one that we use fairly frequently without maybe realizing that we're using it in this way. It starts with a W. It also is describing the force of gravity on an object. It's weight, yes. Okay. And the force of the earth on the object, or the force of gravity, or the weight of an object can be calculated knowing two things. What's one thing that's going to increase the weight of an object? It's mass, right? It's mass. So the force of the earth on, oh my goodness, the object. My crankiness is going to come out. There we go. Is equal to the mass of the object. Okay. And then we're going to multiply it by something. Does anybody know what we multiply it by? The acceleration of gravity, which is negative 9.81. Yeah. So we write that as g, right? Little g, which is, come on, stinker, negative 9.81 meters per second squared. We've known that number. We love that number, right? We are now entering into the time where we're going to use that number, and we need to make sure we understand what it means. What does the negative mean? It's going down. Not only is the acceleration always down, right? Yep, the acceleration is always down. The force of the earth on the object is always which way?
Down.
Down. Always down. Because it's just the acceleration times the mass. Okay. We haven't really defined mass. What is mass? Look at you. You're a rock star. Yeah. The amount of matter in the object, right? Like how much stuff is in it, not how big it is, but how much stuff is in it, right? Because you can have something that's very, very dense that has a lot of mass, or something that's very, very not dense with very, very little mass, even if it's really big. Okay. So now, if you know the mass, and what units are we always going to measure our mass in? Kilograms. Always in kilograms. If you took chemistry and they indoctrinated you wrong. I know, those crazy chemists. So here's a funny thing. The SI unit, have you guys heard of SI before? The System International of Units calls two different things their official unit. For physics, we always, always, always use the kilogram. RAM. That is our base unit. Mrs. Ellickson, when she's teaching chemistry, or Mrs. Hughes, when she's teaching chemistry, would look at that and be like, what? That's 1,000 of the thing I like, right? Because they always talk in terms of grams. Question, why do we disagree? What do you mean?
Those chemists are wrong.
He's trying to earn points, right? Can you tell? That's what I say. The chemists are, no, of course they're wrong. Yeah. Yeah, so it's funny, right? Because the chemists in general are dealing with really little things. So here's the funny part of it, because that's what I've taught for years and years and years, right? And then my eyes were open to the world of particle physics. Wah! And particle physics is on the so chemists deal with molecules and atoms. Like that's their bag, right? They the smallest thing they're gonna do, they're gonna be like, oh, it's a nucleus, or oh, it's an electron, right? The electrons are da-da-da. And they talk about them in terms of grams. But we take those protons and neutrons and break them apart. What? Like that's crazy town. But even when we're talking about the tiniest bits of matter, the elementary particles that make up those things, we still talk about them in terms of kilograms. We still do it in terms of kilograms because all physicists want to be able to talk to each other, right? And if half the physicists are talking in grams or nanograms or, picograms, like it doesn't make any sense. So we talk about it in terms of kilograms. It's just like 10 to the negative big number kilograms. It's just 3 more in your exponent. That's all it is. Those are always in kilograms. I take my water bottle and I place it on a triple beam balance. Do you guys know what a triple beam balance is? You've seen a triple beam balance before? Do you remember that thing? Yeah? What's it measuring? The water bottle.
No, I was like gonna do that. No mind.
It is the mass.
I was gonna do
Wait, one more time?
that. Never mind.
Are you sure? Okay. I was trying to read your mind.
Going too deep.
It measures the mass because it's balancing, right? Okay. I measure the mass of this. I say that this is 1 kilogram, let's say. Okay. So I have the mass of my water bottle. I'm going to go on a trip. I'm going to go to the moon. Yay! I got to take my water with me, right? Because, I got to stay well hydrated no matter where you're at. Take my water bottle. I don't, drink any of the water in transit because why would you do that? And so I have it on the moon and I find its mass. And what's its mass going to be? Is it going to be 1 greater than or less than 1 kilogram?
What?
The mass on Earth was 1 kilogram. What do you guys think back there?
I'm confused on the question.
Okay, let me write down and pose the question more clearly. So here's my water bottle. Me? What are you talking about? What?
No,
Oh.
probably.
I was gonna say what? Okay, so on Earth, the mass is equal to 1 kilogram. I'm gonna take that water bottle, I'm gonna move it to the moon. My question is, on the moon, what's the mass of my water bottle? Is it greater than, less than, or equal to 1 kilogram? Why are we saying less?
Because there's no gravity on the moon.
Oh, I love this conversation. I love this conversation. All right. No, I'm just trying to see where we're at. Is there gravity on the moon?
I thought there wasn't gravity on the moon.
There is just less than
So have you heard about Alan Shepard, right? He was that astronaut that took the feather and the hammer to the moon. Have you heard this story before? Oh my gosh. No, you've never heard. I'll have to pull it up. I don't know if we have time to do it. I don't know if we have time to do it right now. But okay, so let me tell you the story. In 19-something, I don't remember when, he took a feather and a hammer to the moon, and he said, okay, let me ask a question. Have you seen a picture of somebody, Neil Armstrong, walking on the moon?
Yeah.
Yeah.
Okay, so Neil Armstrong walked on the moon, right? Oh man, I was totally gonna make a point. That's too bad. I'll have to start there next time. Until, write that down. Neil Armstrong walking on the moon. That's what we'll start next time.
Well, you can just do it.
No.
I'll pull it up tomorrow.